Tonight, we're going to explore one of the most unforgiving journeys across our solar system. Take a single human being and set them down on every world in turn. First with no protection, then inside the best suit we can build, and measure two things: how long they last and what kills them first. On March 1st, 1982, a Soviet lander called Venera 13 touched down on Venus and lasted 127 minutes before the heat destroyed it. That number became the benchmark. Against it, the human times are hard to take in. 10 hours on Mars, 2 minutes on Neptune, and what ends you is almost never what you would guess. Not the cold, not the fire. On Venus, the pressure crushes you before the heat can finish the job. By the end of tonight, you're going to understand why not a single world will simply keep you alive. Why the fastest deaths and the longest survivals fall where you would not expect. And what it would take to turn a place that kills in minutes into somewhere a stubborn species could call home. Before we get started, take a second to like and subscribe if you enjoy these videos. It really helps a lot. Now let's begin. The first stop is not the hardest world. It is the gentlest one. And that is on purpose. Mars is where it begins, at the equator, close to the flat, boulder-strewn ground where NASA's Curiosity rover set down in Gale Crater. The rock is rust-coloured, the dust drifts low across it, and the sky overhead is a pale butterscotch instead of blue. It reads less like an alien world than a cold, dry, high-altitude desert on Earth, closer to the Atacama or Antarctica's dry valleys than to any sand dune. It looks almost homey. That is exactly what makes the hidden danger land harder later. The temperature is the first surprise. On a Martian summer day at the equator, local noon can feel like room temperature, close to 20 degrees Celsius, mild enough that a suit's thermal protection barely has to work. But Mars cannot hold onto that warmth for long. The moment the sun drops, the temperature falls toward minus 70 degrees Celsius, and across the whole planet the range runs from about minus 153 degrees Celsius at the winter poles up to that same mild 20 degrees at the summer equator. The warmth is a narrow window, skin deep, midday only. Stranger still, at that same equatorial noon, the air holds so little heat that it can feel like 24 degrees Celsius at your feet and 0 degrees Celsius at your head. At the same moment, in the same body, warm ground, freezing air an arm's length above it. There is almost no atmosphere here to carry that heat upward and even it out, so the two temperatures simply sit stacked on top of each other, refusing to mix. Gravity is the second relief. Mars pulls at about 38% of what Earth does. So a person who weighs 150 pounds at home weighs about 57 pounds here, and can jump roughly 3 times as high. Even a heavy suit starts to feel almost weightless. Movement is loping and easy, the kind of walk that costs far less effort than it should. None of that comfort changes what the air is made of. The Martian atmosphere is about 95% carbon dioxide, the same gas that leaves your body every time you breathe out, with only a trace of nitrogen and argon, and a sliver of oxygen too small to use. Surface pressure sits around 600 pascals, under 1% of what you would feel at sea level on Earth. There is nothing here to breathe, and almost nothing here to hold radiation off. That second failure is the slow killer, and it does not announce itself. Mars has almost no global magnetic field, and an atmosphere roughly 100 times thinner than Earth's. So cosmic rays and solar particles reach the ground nearly unfiltered. Curiosity's onboard radiation detector has measured a surface dose of roughly 0.64 to 0.67 millisieverts a day. Millisieverts being the unit that tracks how much radiation a body actually absorbs. Carry that forward across a full year, and it adds up to about 230 millisieverts, on the order of 100 times what the cosmic ray background delivers to Earth's surface. During a solar flare, it climbs higher still. you would not feel any of it happening. Wait, this is a planet that damages machines the same quiet way. Curiosity's own aluminum wheels have been punctured and cracked by sharp buried rock since 2013, with 2 tread segments breaking outright in 2017. And yet, the rover kept driving, past 32 kilometers of total distance, because it runs on a plutonium power source instead of solar panels. The same difference that let it survive the global dust storm of 2018, while the sun-powered Opportunity rover went dark and never woke again. A machine built for this world still gets worn down by it. A person in a suit should expect the same, only slower and quieter. The suit itself is built from Kevlar and polyethylene, hydrogen-rich materials that block radiation more effectively per kilogram than any metal shielding could manage. Wear it here, and for the first several hours, nothing goes wrong. No struggle, no alarm, no moment where the suit strains to keep up. It would be easy to relax into that, to start thinking about digging in and staying. But here's where it gets strange. Comfort on Mars is not the same as safety. Not a close call, not a near miss. A long stay here quietly wrecks the body while it feels like nothing is happening at all. Low gravity and steady radiation work together, degrading circulation, raising the risk to the heart, dulling the brain over months instead of hours. Modeling suggests bone density drains at roughly 0.22% a week in Mars gravity. Carry that forward across a year, and more than a tenth of the skeleton is simply gone. None of it hurts until the stay is already over. No one has ever lived in gravity this weak for years at a stretch. So that 0.22% figure comes from a model built on microgravity data, not a measurement anyone has actually taken on Mars. Whether Martian gravity is enough to meaningfully slow that damage, or barely different from none at all, is a question nobody can answer yet. None of that catches up with you inside the time frame of this stop. After about 10 hours, the oxygen supply simply runs out and you climb back into the spacecraft alive. Mars is the only world in this challenge that ends with a return trip instead of a body left behind. That is not mercy. It is a debt with a delayed due date, and it sets the benchmark every world after it will fall short of. Every stop from here on spends less time being kind before it stops being kind at all. The next stop keeps that promise in the worst way it can. This is the second world in the tour, and it is not a gentle step down from the first. Mars let a person leave. Venus has let almost nothing leave, not for long, and one Soviet machine proved exactly how long really is. On March 1st, 1982, a lander named Venera 13 touched down on the surface of Venus, the most unforgiving planet in the solar system, and transmitted for 127 minutes. That is nearly 4 times its design life of just 32 minutes. It sent back the first colour photographs ever taken from another planet's surface, and the first sound ever recorded on another world. Then heat pushed its electronics past what they could survive, and the signal stopped. Venera 13 did not survive by being tough. It survived by carrying its own cold. Engineers sealed its instruments inside blocks of lithium nitrate, a salt that soaks up enormous heat as it slowly melts. A passive buffer racing a clock it could not win. At its landing site, the probe recorded 457 degrees Celsius and about 89 atmospheres of pressure before it finally died. That is the number every survival time in this challenge gets measured against from here on. Not minutes borrowed from luck. Minutes bought with a block of slowly melting salt and nothing else. 127 minutes. From a machine engineered to survive Venus and nothing more. Drop a person here with nothing but skin between them and the air, and the ending arrives almost immediately, faster than the mind has time to register that anything has gone wrong. Here is the tour's first great reveal, the kind Mars never gave a chance to appear. The obvious killers announce themselves plainly: the 465-degree heat and the drifting sulfuric acid clouds overhead. Neither one gets there first, pressure does. Venus's surface pressure runs about 92 to 93 bar, roughly 92 times what Earth carries at sea level. The same crushing weight as standing nearly 900 meters underwater, about 3,000 feet down, deeper than any human diver has ever gone. It is the same as a small car resting its entire weight on a single thumbnail. That pressure collapses every air-filled space in the body at once. The lungs go first, the sinuses go with them, both in the same instant, before pain even has time to register. Not the heat, not the acid, the weight of the air itself, faster than 465 degrees, could ever finish the job. No one has ever tested this on a living body, human or animal. So pressure winning that race is drawn from deep sea diving injuries and burn research, not from a measurement anyone has actually taken on Venus. Now, put on the best suit ever built for this world. A Venera-grade shell of reinforced titanium plating rated to 90 atmospheres. Venus's gravity is only about 10% weaker than Earth's, so the suit barely feels heavier than it would back home. And walking feels almost ordinary, even as everything around you is not. Around the visor sits a dense yellow-orange gloom. Thick carbon dioxide laced with sulfuric acid. Sunlight scattered down into a permanent twilight over flat volcanic plains, stretching farther than the haze will let you see. There is no wind sound you can hear over the suit's own systems, no shadow sharp enough to tell you where the light is coming from. Just gloom in every direction. Call it what the source data calls it. A hellish greenhouse, closed on every side with no door out. The heat itself is the second reveal, and it does not behave the way heat should. Venus's average surface temperature runs about 464 to 467 degrees Celsius, hot enough that lead, tin, and zinc exist here only as puddles of liquid metal, never as solid rock. Picture standing on ground already hot enough to pool metal, and never once finding it cooler underfoot, no matter how long you wait. On Earth, night brings relief from a scorching day, a drop you can feel within minutes of the sun going down. Here it barely does. The night side of Venus sits at about 450 degrees Celsius, the day side at roughly 467 to 474. A gap of only tens of degrees between the darkest hour and the brightest. Not a cool planet after sunset, not even a mild one. Nearly the same furnace, all the way around the clock. Day folding into night, without ever loosening its grip. Why would a planet's dark side stay almost as hot as its lit one? The answer is not the sun cooking the ground directly. It is the whole sky, closing in like a lid that never lifts. Sunlight strikes the surface, and the surface releases that heat back out as infrared, invisible heat radiation. But the atmosphere here is about 96.5% carbon dioxide, thick enough to catch that infrared before it can escape and send a large share of it straight back down. Fierce winds carry whatever heat does, slip through all the way around the planet, smoothing away the difference between day and night before it can ever open into real relief. Here's what a greenhouse effect looks like on a milder world. A noticeable gap between day and night, however small. Venus erases even that. That is the greenhouse effect, carried to its extreme. A blanket that never lets the room cool down, on either side of the planet, at any hour. The suit fights this on two fronts at once. A silicon carbide layer, a hard ceramic shell, coats the outside and is rated to withstand around 500 degrees, while liquid coolant runs through the suit's interior, carrying heat away as it slowly evaporates. Titanium plates beneath that shell are coated in tantalum and gold to resist the acid drifting through the air, metals the acid cannot easily eat through. For a while, it works. For a while is not forever. The air itself is strange in a way no household object quite captures. Above 31 degrees Celsius and about 73 atmospheres of pressure, carbon dioxide stops behaving like a simple gas and becomes what scientists call a supercritical fluid, something between a gas and a liquid at once. Venus's surface sits far past that threshold on every measure, so the carbon dioxide around the suit fills space the way a gas does, but presses and dissolves the way a liquid does. Not air, not fog, not steam, something closer to a dense, invisible ocean that happens to be a gas. Exactly what that does to living tissue on contact is not well mapped either. A real gap between the physics and any survival estimate built on top of it. Eventually the suit loses 2 fights at the same time. Cooling fails first. Heat stroke sets in fast, internal temperature climbing toward a critical point in about a minute, and consciousness goes with it. While that happens, acid and pressure work on the structure from the outside, cracking seams and buckling plates until the suit itself starts to fail alongside the body inside it. Survival time, fully suited, about 20 minutes, far past Venera 13's original 32-minute design life. Far short of the 127 minutes the real probe actually bought with its own melting salt. In a standard NASA suit, built for far gentler worlds, a person would not have lasted even 1. Set the 2 numbers side by side. A machine with no heartbeat to protect, carrying its own block of melting salt, bought 127 minutes. A person wrapped in the best shielding the titanium, ceramic, and gold can offer buys about 20. Venera 13 was never trying to keep anyone alive. It only had to keep transmitting. A human body asks for more than a signal, and Venus charges accordingly. 2 stops into the tour, and the gap between them is already staggering. 10 hours on the gentlest world, 20 minutes on the harshest one so far. A drop that's steep, this early in the challenge, makes one thing clear. There is no smooth curve from mild to deadly, no orderly ranking by distance from the sun. Each world sets its own rules, and the tour has barely begun learning them. Far worse waited ahead, and far stranger too, worlds where the thing that ends the visit would not be heat, or pressure, or acid, but something almost nobody watching would ever guess was coming. On Venus, the planet decided how you died. Pressure won the race before heat or acid ever got a vote, and there was nothing to do about it once you landed. On the 3rd stop, the choice gets handed to you instead, in the first few seconds, by nothing more than which way you happen to be facing when you touch down. Mercury is the closest planet to the Sun, and the smallest in the solar system, and here fate is decided before you do anything at all. Land on the dark side or land on the sunlit side, and the whole visit runs differently from that single accident of geometry. There is essentially no atmosphere here, only a thin exosphere, a scattering of atoms knocked loose from the surface by the solar wind, far too thin to trap heat, carry it, or share it anywhere. Earth's air moves warmth around constantly, evening out the difference between a shaded porch and a sunlit yard. Mercury has none of that machinery. With nothing to hold warmth in place or spread it around, Mercury swings between the widest temperature extremes of any planet in the solar system, from about minus 180 degrees Celsius at night to about 430 degrees Celsius by day. A swing of more than 1,000 degrees Fahrenheit, averaging out around 167 degrees Celsius. No other world runs that hot and that cold within the same rotation. Appear on the dark side and the ground is savagely cold. And because there is no air to carry that cold toward you or away from you, it feels strangely inert. More like touching frozen metal in a sealed room than standing in a biting wind. Nothing moves. Nothing howls past the visor. No wind ever will, on a world with no air left to carry one. The land looks almost exactly like the moon's. Grey craters overlapping grey craters. long cracks running through ancient rock, a fine blanket of dust undisturbed by any breeze, lit only by faint starlight with nothing overhead to soften it or warm it. Here the fatal instinct sets in. Wait it out. The sun will rise eventually, and the warmth will come back with it. That instinct is the first mistake of the stop, and it is not a small one. A Mercury solar day, one sunrise to the next, does not run on the planet's spin the way it does back on Earth. Mercury is locked into a 3-2 spin orbit resonance, spinning on its own axis 3 times for every 2 full trips it makes around the sun, and the 2 motions layer together into something stranger than either alone would produce. One orbit around the sun takes 88 Earth days, but a single sunrise to the next sunrise, the day a person standing on the surface would actually live through, stretches to 176 Earth days, nearly 6 months. Not a long wait, not a wait anyone can survive on a fixed air supply. No one waits out a 6-month night. So the sun rises eventually on whatever schedule it keeps, and when it finally does, it is punishing. With no atmosphere to filter or soften anything on the way down, the sun itself appears blinding white and about 3 times larger in the sky than it does from Earth, close enough that it fills a noticeably wider slice of the view. The light hitting the ground is roughly 7 times more intense, somewhere near 9,000 watts per square meter, against Earth's familiar 1,360. Mercury barely shields you from any of it either. Its magnetic field measures only about 1% the strength of Earth's, a shield so thin it barely counts as one at all, and the solar wind striking this close to the sun carries 6 to 30 times the pressure it carries back home. During strong solar events, that pressure can push the magnetic field down until it presses against the surface itself, letting charged particles from the sun strike the ground directly, with nothing standing between them and you. No one has strapped a living body into a suit on Mercury's surface and logged what the radiation dose actually does to it, minute by minute. The mechanism is well understood: no atmosphere, no ozone layer, occasional direct solar wind bombardment, but the precise numbers, exactly how many minutes before organs fail, are drawn from that mechanism, not from a measurement anyone has taken there. Even the sunlight multiplier itself gets argued over in different sources, 7 times brighter in some, 10 times in others, though the physics keeps pointing back towards 7. The suit built for this world is rated against radiation, and that part of it holds exactly as designed. What fails is the cooling. Solar radiation works its way into the suit's electronics and begins disabling them one system at a time, while that same radiation delivers a lethal dose straight into the body, and internal organs begin to fail well before the mind has time to understand what is happening. Cooling shuts down next. Then comes the collapse. Not suffocation, not a torn seal or an empty tank somewhere in the pack. The oxygen supply is still intact when it ends, full and untouched, sealed inside a suit that failed for entirely different reasons. Radiation first, heat right behind it. Survival time here, about 15 minutes, on a world where night lasts 6 months, and there is nowhere within reach to hide from either side of that clock. 2 stops past Mars, and the numbers have already collapsed, from 10 hours, down to 20 minutes, down to 15. NASA's Messenger probe spent years mapping this scorched, airless little world in painstaking detail, orbiting close enough to log exactly how brutal that swing between the 2 sides really is. The same swing a person standing here would have to survive without any atmosphere standing between them and it. What it found only confirms the shape of the problem: a world with no middle ground anywhere on its surface. There is no gentle half of Mercury waiting to be discovered. There is no mild hour, no comfortable stretch of the day, no shaded valley that splits the difference between the 2 extremes. There is only the side about to kill you slowly, and the side about to kill you fast. And the tour was only just getting started with worlds that punish a wrong guess this quickly. Every stop so far has given you somewhere to stand. Rust and dust on Mars. Scorched rock under a titanium suit on Venus. Cratered ground, one side burning, one side frozen, on Mercury. The fourth stop takes even that away. Jupiter is the largest planet in the solar system, and it starts killing you before you ever reach it. Its magnetic field is about 20 times stronger than Earth's at the cloud tops. But that number understates the problem. The field's total strength, what scientists call its magnetic moment, a measure of how much space the field actually dominates, is roughly 20,000 times larger than Earth's. So it traps a volume of space far beyond anything a simple strength comparison suggests. On the side facing the Sun, that invisible magnetic shield averages about 5.3 million kilometers across, roughly 150 times wider than the planet itself. If it somehow glowed the way an aurora does, it would look 2 to 3 times the size of the full moon in Earth's sky, and that is seen from a distance measured in hundreds of millions of kilometers. Its tail trails backward at least as far as Saturn's orbit, one planet's magnetic shadow reaching across a second planet's entire path around the Sun. None of this is scenery. Any ship approaching Jupiter has to cross that shadow before anything else about the planet even becomes a problem. Radiation first, everything else waiting behind it. Inside that shield sit belts of radiation lethal on a scale that is hard to hold in the mind. The first probes to ever fly past, Pioneer 10 and Pioneer 11, absorbed doses roughly 1,000 times what would kill an unshielded person, and they were only passing through. NASA's Juno spacecraft survives its orbits today only because its electronics sit sealed inside a titanium vault, about 180 kilograms of centimeter-thick walls built around the most sensitive parts, cutting the radiation those parts receive by roughly 800 times. Take the vault away and the mission ends in hours. Only a hull built the same way, thick and metal and unglamorous, keeps your ship intact long enough to arrive at all. Nothing about a human body improves on that math. No suit anyone has built shields flesh and organs the way a spacecraft's hull shields electronics. So every extra minute inside those belts spends down a body's tolerance for radiation a little faster than the one before it. And then you arrive, and there is nothing beneath you. No crust, no rock, no line where sky quietly becomes ground the way it does everywhere else in the tour. Descending, you drop through cloud decks stacked by pressure instead of by altitude the way clouds stack back on Earth. Visibility runs close to nothing, an orange-brown haze in every direction, no horizon because there is no ground anywhere to draw one against. First, an ammonia ice layer, thin and brutally cold, sitting at a pressure of about 0.7 bar, less than what you would feel at sea level on Earth, and a temperature near minus 140 degrees Celsius. Then a middle layer of ammonium hydrosulfide, near 2 bar, a chemical name for a smell you would recognize instantly, unmistakably, rotten eggs. Then water ice and water vapor, deeper still, at a pressure of about 5 to 7 bar, roughly 6 times what you would feel standing at sea level back on Earth, close to what a diver feels 50 meters down. The 3 layers together span about 71 kilometers of open, structureless falling, nothing to grab, nothing to land on. As the cold ammonia gives way, the temperature climbs, and the pressure keeps climbing with it, first towards something like Earth's, then far past it. The winds do not slow the fall down gently. Jupiter's regular jet streams blow at about 360 kilometers an hour, and the edge of the Great Red Spot, a storm larger than Earth itself, exceeds 640, faster than any hurricane this planet has ever produced. The winds do not simply push, They catch the body and throw it into a vortex, and the forces inside that vortex tear it apart, not survivable by training, not survivable by strength, only avoidable by never happening to a person at all. The suit keeps falling. It's empty now. It keeps falling anyway. But here's where it gets strange. Lightning finds you too, and not gently. Individual bolts here run more than 100 times as powerful as anything Earth storms produce, born from clouds that tower more than 100 kilometers high, roughly 10 times the height of the tallest thunderheads on Earth, according to research reported as recently as March 2026. The suit, alone now, drifts on past a final water cloud layer near freezing and keeps going, deeper than anything carrying a body has ever gone. 4 stops into the tour, and for the first time, nothing kills you by touch. Not heat against skin, not cold seeping through a seal, not pressure crushing a chest. Here it is, speed and force alone. How do you even put a number on survival in a place with no bottom to hit? The 3-minute estimate sounds like it was picked out of the air. It was not. On December 7th, 1995, the Galileo probe entered this same atmosphere at more than 106,000 miles an hour. The fastest atmospheric entry any spacecraft has ever made, decelerating at about 230 times the force of gravity on the way in. Fighter pilots black out below 10 G. There is no training, no seat, no suit built for a body that experiences 230. Galileo endured it anyway, sealed behind a heat shield that reached nearly 16,000 degrees Celsius on its surface, roughly twice as hot as the surface of the sun itself. The shield itself was designed to be sacrificed, burning away layer by layer, so the instruments underneath stayed intact a little longer. It kept transmitting through all of it. For about 57 to 61 minutes, reaching a depth of roughly 150 to 180 kilometers, it sent data back up through that same storm, a small metal probe reporting from inside a planet most of us will only ever see as a bright point of light in the night sky. Then it fell silent, at a pressure near 22 times sea level and a temperature near 150 degrees Celsius. Not a guess. Not a rounded number with nothing behind it. The exact band where the only machine ever sent to check stopped talking. Below that depth, nobody knows. No probe has gone deeper and reported back. Whatever exists past 22 bar has never been confirmed by anything, only modeled from the outside, guessed at from what the deep interior should look like if the models are right. The body never makes it that far. Wind and force finish the job long before 3 minutes are up, well before the suit could ever reach Galileo's final depth. What continues downward afterward is empty. It falls through the same cold, the same crushing pressure, the same absolute dark, all the way to the band where Galileo went quiet, and then past it, into the part of Jupiter no machine has ever mapped, and no signal has ever returned from. Somewhere in the same neighborhood, one of Jupiter's own moons is about to offer something the planet itself never could. Solid ground. Europa arrives first, and after nothing underfoot but falling, solid ground feels like mercy. It is a frozen moon, about 90% the width of Earth's own moon, its face scarred by long straight cracks that run for hundreds of kilometers, some of them longer than entire countries back home. The ice throws back about 5.5 times more sunlight than the moon does, so from a distance it does not look grim at all. It looks bright, almost polished, a pale mirror hanging near the planet that just tried to kill you. For a moment, after 4 stops of heat, crushing pressure, and a bottomless fall, this looks like the gentlest place in the entire tour. The cracks running across the ice are not random. They stretch in long, straight, oddly deliberate lines, some crossing others at sharp angles. The kind of pattern that looks engineered even though nothing built it. Nothing moves. No wind, no dust, no sound but the suit's own systems. After Jupiter's chaos, the quiet itself feels like a reward. Under that brightness sits something enormous. In December 2025, Juno's measurements set the ice shell at about 29 kilometers thick, give or take 10, roughly 3 Mount Everests stacked one on top of the other, base to summit to base again. Beneath that shell waits a global ocean of salt water, modeled at around 3 billion cubic kilometers, a little more than twice all the water in every ocean on Earth combined. It is, by volume, the largest body of liquid water known anywhere in the solar system, and it sits directly under your boots. 29 kilometers does not sound like much on paper, until it is measured in ice instead of air between your boots and an ocean that dwarfs every sea this planet has to offer. Daytime temperatures at the equator can reach about minus 143 degrees Celsius, nearly as cold as Mercury's dark side, and gravity here is gentler than anywhere in the tour so far, about 1/7 of Earth's, roughly 0.13 g, weaker even than the moon's own weak pull. Walking is almost effortless, a slow bounding glide across ice that groans faintly under the suit's weight, each step carrying farther than it would anywhere back on Earth. Then comes the detail that should change everything about how this stop feels. Jupiter's radiation still reaches this far, and it does something strange to Europa's ice. It splits the water molecules apart, hydrogen and oxygen torn loose from each other in a process called radiolysis, breaking water down using radiation instead of heat or electricity. The light hydrogen drifts off into space almost immediately. The oxygen stays, and it collects, molecule by molecule, across the whole sunlit face of the moon. In March 2024, Juno measured the rate directly. About 12 kilograms, close to 26 pounds, of oxygen forming at the surface every single second. Not occasionally. Not in some rare event decades apart. Every second, right now, while you stand there. This moon is not just cold and bright, it is manufacturing breathable air continuously, the closest thing to an oxygen factory anywhere in this tour. No engine drives it, no plant, no living thing, just ice, sunlight, and the same radiation that crossed the belt your ship had to survive on the way in, quietly rebuilding the one thing every earlier stop on this tour has been missing. The picture did not hold. None of that oxygen will save you. The same radiation splitting the water apart is striking your body and your suit at the same time, delivering a surface dose of about 5,400 millisieverts a day. There is no everyday object that dose compares to easily. The number that does compare is worse. Doctors call about 4,000 millisieverts the LD50, the dose that kills half of the people exposed to it. Europa's surface delivers well past that number, and it does it every single day, not as a one-time event, but as a standing condition of the place. An unshielded person absorbs a lethal amount within hours. Spacecraft electronics fare barely better, which is why any lander built for Europa seals its most sensitive parts inside a shielded vault, the same instinct Juno used at Jupiter itself. Not a shortage of oxygen, an abundance of it, sitting under a radiation field lethal regardless of how much air is in reach. You might catch sight of a plume first, a jet of water vapor thrown high above the ice, silent and slow in the low gravity. Hubble has spotted these near the South Pole, reaching roughly 200 kilometers up. Taller than the moon's own ice shell is thick. It looks like the kind of thing that should worry you. A geyser on a frozen world, water reaching for space. It is not. No plume reaches you in time to matter. The radiation gets there first, disabling the suit's oxygen system from the inside, then turning on the suit itself, breaking down the same seals and circuits that were keeping you alive a moment earlier. Your legs go first, then your vision, then nothing. Survival on Europa. About 15 minutes. The same number as Mercury, on a moon that spends every one of those minutes still making the very air you're dying without. Line the tour up so far, and the numbers refuse to settle into any pattern. 10 hours on Mars, 20 minutes on Venus, 15 minutes on Mercury, under 3 minutes falling through Jupiter, and now 15 minutes again, on the one stop that looked, for a little while, like the safest since Mars. Whether those plumes are frequent, dependable geysers, or rare, faint bursts that only sometimes reach that height, is still an open question. A 2024 analysis concluded that if they are real, they are fainter and less frequent than early images suggested. And whether any of that radiolytic oxygen ever reaches the ocean below, seeping down through 29 kilometers of ice to reach the very water it was made from, is not known either. It is one of the reasons scientists still call Europa one of the most promising places in the solar system to look for life, and one of the cruelest, since the same energy that might feed something down in that ocean is exactly what would kill anything standing on the ice above it. 5 stops down, and the shape of the danger keeps changing every time. Mars killed slowly and quietly, Venus by crushing, Mercury by a fork in the road, Jupiter by force with no ground to land on. Europa kills by irony, offering the one thing every earlier stop denied you, and taking your life for it anyway. Under its ice, an ocean twice the size of every sea on Earth waits closer to the surface than most oceans are to open sky, sealed away by radiation instead of distance. There is more falling still ahead. The fall waiting on the far side of Europa looks almost exactly like the one that came before it. Saturn announces itself the way nothing else in the tour has. A wide gold disk wrapped in rings visible from farther away than any other planet allows. Bands of ice and rock catching light. The ship crosses on its way in. But underneath that famous shape, the truth matches Jupiter's exactly. No surface, no line where sky quietly becomes ground. Only curiosity explains why anyone makes this fall a second time, in a reinforced radiation suit, into layer after layer of gas with nothing solid waiting at the bottom. High in the atmosphere, you cross an aurora, and it holds a quiet oddity nobody mentions in the photographs sent home from orbit. Saturn's aurorae glow only in ultraviolet, invisible to the human eye. Their colours run red at the bottom and purple at the top. The exact reverse of Earth's own aurora, where green and violet sit closest to the ground. Not a light show built for human eyes. A light show built for instruments that can see light we cannot. It plays overhead for the entire fall, curling and brightening the way the northern lights do back home, and you will never once see it. The clouds arrive in layers, the way they did at Jupiter, only colder. An upper deck of ammonia ice sits between half a bar and 2 bars of pressure, somewhere around minus 173 to minus 113 degrees Celsius. At the 1 bar mark, the level scientists use as Saturn's reference surface, the temperature holds near minus 138 degrees, cold enough that nothing at this level has ever once been warm. Deeper still, a water ice layer runs to about 9.5 bar, and only far down, past 10 to 20 bar, does the temperature finally climb into a range where water can exist as droplets mixed into ammonia, a hidden layer no probe has ever reached intact. You will not get there. The winds here are among the fastest anywhere in the solar system. Saturn's equatorial jet peaking near 500 meters a second, close to 1,800 kilometers an hour, roughly twice the cruising speed of a passenger jet back home. And there is no mountain range or ocean to slow it down, only open gas for the wind to run through unopposed. Near the reference surface, the cold reaches the suit first. Ice creeps across the visor, then across the electronics underneath it. The rising pressure finishes what the cold started, bending the shell, then breaking it. Survival falling into Saturn, about 5 minutes, a little longer than Jupiter gave you, but the shape of the ending is the same. 6 stops down, and this one barely counts as a death of its own. It is Jupiter's death again, only slower by 2 minutes. Then, Titan, and after 2 falls with nothing at all beneath your boots, solid ground again feels like an actual mercy. It is the only moon in the solar system with a real atmosphere. About 95% nitrogen and 5% methane, roughly 4 times denser than the air over your own backyard. Surface pressure runs 45 to 60% higher than Earth's, close to what a diver feels standing in 15 meters of water. A weight you notice in your chest before you notice anything else. Gravity is gentle here, about 14% of Earth's. So even a heavy suit moves easily. A slow, bounding walk across a plain lit by nothing but a thick orange haze. The haze is not weather in the way clouds are weather. It is a permanent smog of organic compounds built up over billions of years. Thick enough that you cannot see Saturn from the ground, cannot see the sun as more than a smear, cannot see anything past the haze at all. Then you notice the lake. It sits low and flat and silver under the orange sky, with what looks like a shoreline, a delta, even a scatter of rounded stones at the water's edge, and for one unguarded second it looks exactly like a lake back home. Wait, nothing on this moon is water. Titan seas and rivers run on liquid methane and ethane, kept liquid only by the deep cold, fed by actual rain falling from actual clouds, evaporating and condensing and falling again in a cycle that mirrors Earth's all the way down to the shoreline. Weather built entirely out of natural gas instead of water. Its largest sea, Kraken Mare, runs at least 100 meters deep and stretches close to the combined size of all 5 of Earth's Great Lakes. About 70% methane by measurement, the rest ethane and dissolved nitrogen. Not water, never water. Do not touch it. Titan itself is bitterly cold, about minus 179 degrees Celsius, and the suit answers with reflective plating and a silica aerogel insulator, the kind of material built to hold almost no heat at all against a vacuum. Radiation this far from Saturn's belts is manageable, survivable in a way nothing has been since Mars. For over an hour, the suit simply holds. You could almost forget for that hour that you were standing on one of the coldest surfaces in the tour. Then the cold finds its way in anyway. Thermal protection finally loses its long argument with minus 179 degrees, and about half an hour later comes unconsciousness. Then hypothermia. A slower death than any gas giant has offered. Survival on Titan, about 2.5 hours. Longer than anywhere else in this tour. Longer than Mars. Longer than every stop between Venus and here added together. The outer solar system was supposed to get faster at killing you, not slower, and Titan breaks that pattern completely. That changed on January 14th, 2005, when the real Huygens probe made the first landing ever achieved in the outer solar system, dropping through this same orange haze on a parachute, and kept transmitting for about 72 minutes from a surface scattered with smooth, rounded pebbles of water ice, a landscape a river might have shaped if the rivers here ran anything but methane. It went silent, but it proved the ground beneath the haze was solid enough to land on, and soft enough to survive landing on, decades before anyone wrote a suit rated to walk across it. 7 stops into the tour now, and the numbers still refuse to settle into a pattern. 10 hours on Mars, 20 minutes on Venus, 15 on Mercury, under 3 falling through Jupiter, 15 again on Europa, 5 minutes falling through Saturn, and now 2.5 hours on a moon, colder than almost anywhere else you have stood, wrapped in an atmosphere thick enough to make that cold feel almost survivable, and dense enough to hide an entire ocean's worth of methane rain, and never once let it freeze solid. 2 gas giants remain, and past them, a pair of moons where the danger stops being heat, or cold, or pressure at all. Past Titan the dark keeps going, and it keeps getting colder until the ship reaches a pale, bluish-green ball, turning slowly on its side, spinning almost like a rolling marble instead of a spinning top. This is Uranus, and it plunges you into another gas giant fall, the third one of the tour. No surface here either, only gas stacked on gas, and one number waiting at the bottom of it that nobody predicted. Uranus sits roughly 1 billion miles closer to the Sun than Neptune. By any ordinary logic, that should make it the warmer of the two ice giants. Closer to the furnace, further from the deep cold of the outer dark. It is not. Uranus holds the coldest temperature ever directly measured anywhere in the solar system, close to minus 224 degrees Celsius, colder than liquid nitrogen, colder than any laboratory freezer built on Earth, colder than Neptune itself. The reason is not distance. Every other giant planet still radiates leftover heat from its own formation, a slow furnace running since the solar system was young. Uranus, alone among the four, barely has one. Whatever warmed its interior billions of years ago has almost entirely leaked away, and nothing rose up from underneath to make the fall gentler. Not a slightly colder world than its neighbor. The coldest one ever recorded. Full stop. With nothing else in the solar system coming close. Nothing does. The winds here move close to 900 kilometers an hour, near the cruising speed of a passenger jet. Except this wind never lands and never lets up. Hour after hour, mile after mile of open gas with nothing to slow it down. No thermal protection built keeps pace with that combination. Extreme cold pressing in from every direction, while the atmosphere itself works at tearing the suit apart, seam by seam, layer by layer. The fall lasts about 3 to 5 minutes before it ends. One of the shortest stays in the entire tour, on one of the coldest worlds in it. Almost everything known about this planet comes from a single pass. Voyager 2 flew by on January 24th, 1986, the only spacecraft that has ever gone there, and 40 years later, it is still the only spacecraft that ever will have, until someone builds another one and sends it out this far. What it saw was strange, mostly for what it did not see. No storms churning the cloud tops, no banding, no swirling spots, nothing like the violence photographed at Jupiter or the layered gold calm at Saturn. Just a smooth, nearly featureless turquoise ball, quiet on the outside in a way that gave away nothing about the cold sitting underneath it. What else might a single 40-year-old glimpse be hiding about a world this far from home? The moons offer something the planet cannot, an actual escape from falling. And they trade one danger for a completely different one. Titania, the largest of them, has a radius of about 788 kilometers, roughly half the size of our own moon, and a surface gravity of only about 0.371 meters per second squared, close to 3.8% of Earth's pull. A person who weighs 175 pounds at home would weigh about 7.6 pounds standing on Titania, closer to 9 pounds once the suit is added. Walking does not feel like walking anymore. It feels like drifting, with your feet occasionally touching down to remind you where the ground is. Every stride carries further than it should, and every landing arrives softer and later than the body expects. Miranda takes that idea even further still. It is the smallest of Uranus's major moons, a radius of only about 236 kilometers, and its surface gravity measures roughly 0.076 meters per second, squared, about 0.8% of Earth's. Total suited weight here comes to just over 2 pounds. An astronaut who weighs more than 200 pounds back home would weigh about 1.5 pounds standing on Miranda's ground. The gravity is so weak that a rock dropped from the edge of Miranda's tallest cliff takes a full 10 minutes to reach the bottom. 10 minutes falling for a single rock. A careless step off that same cliff would not end the way a fall ends anywhere else in this tour. It would not end quickly at all. Enough force in the wrong direction, and you do not fall toward the ground. You drift away from it, out past the edge of the moon, toward the open dark, with nothing left to pull you back. These two stops do not kill on a clock the way everything before them has. Mars gave you 10 hours, Venus gave you 20 minutes. Even the fastest falls gave you a number counting down to 0. Titania and Miranda do not work that way. The danger here is not speed, and it is not cold. It is the quiet failure of a rule you never had to think about anywhere else, that a world holds you to its surface. On these two moons, that rule barely applies at all. And it is worth remembering because the second half of this journey will spend most of its effort trying to build a wall against exactly this problem, and will not fully manage it until the very end. Even the one flyby that taught us all of this may not have told the whole story. A 2024 reanalysis of Voyager 2's 1986 data suggests the probe arrived, while Uranus's magnetosphere sat in a rare, compressed state, something that happens only about 4% of the time. 4 decades of textbook description, the only direct look humanity has ever had at this planet, may describe one unusual day rather than an ordinary one. Nobody has been back to check, and nobody knows when anyone will be. 8th stop, and the shape of the danger has changed again. Cold killed you first at Mercury's dark side, wind and pressure killed you at Jupiter and at Saturn, and now, for the first time in this tour, a world's own gravity is barely strong enough to notice that you are standing on it at all. That absence will not stay a curiosity for long. 2 more worlds remain before the survival half of this journey closes, and past them wait a pair of stops even farther out, where the numbers are about to fall lower than anywhere else this journey has taken you yet. 2 worlds remain in the dark, and the first one wears the calmest face of the entire tour. Neptune is a deep, tranquil blue, the kind of colour that looks almost restful, set beside the churning storms back at Jupiter. It sits alone out here, and it has only ever had one visitor. In August 1989, Voyager 2 flew past Neptune, the only spacecraft that has ever reached it, and none has gone back since. That calm is the tour's most complete deception. Below the blue lies a temperature colder than minus 200 degrees Celsius, an atmosphere built from hydrogen, helium, and methane, and winds that beat every other wind recorded anywhere in the solar system. They blow past 1,200 miles an hour, over 2,000 kilometers an hour, gusts that at altitude move roughly 1.5 times faster than sound, travels through Earth's air at sea level, and land at nearly 17 times the wind speed that defines a Category 1 hurricane back home. No one expected a planet this far from the sun, this starved of sunlight, to carry the strongest winds anywhere in the solar system. There should not be enough energy out here to drive anything close to that speed. Radiation out here is weaker than it was at Saturn or Jupiter, but it has not gone away. It is still there, still adding to the damage, not calm, not anywhere close to it. There is no room for a death sequence the way earlier stops allowed, no cooling system failing first, no slow slide toward unconsciousness. The wind alone does the work before anything else in the suite even has a chance to fail on its own terms. Survival on Neptune. About 2 minutes of freefall, the shortest of the entire tour, over before the mind can fully register what is happening. In that same August 1989 flyby, Voyager 2 caught one more thing on its way past. Geysers erupting from the surface of Neptune's largest moon, Triton, throwing icy material more than 8 kilometers up into the black. Dark plumes rising off a moon so cold it barely seemed capable of doing anything at all. Then, the last stop. Pluto sits at the true edge of the challenge, a dwarf planet visited exactly once, after a journey of its own that took nearly a decade to complete. On July 14, 2015, New Horizons became the only spacecraft ever to reach it, measuring Pluto's diameter at about 2,370 kilometers, smaller than our own moon's 3,474, finally settling a debate that had run for decades over what Pluto even was: planet, dwarf planet, or something in between. Pluto keeps a thin nitrogen atmosphere, real but barely there, a surface pressure of about 1 Pascal, roughly 100,000th of what Earth carries at sea level. That thin air offers only the faintest protection from radiation. It can slow down the weakest solar particles on their way in. It does nothing at all to the fast ones, the high-energy cosmic rays that pass through it, as though the atmosphere were not there. Limited shielding, not real protection. Out here, sunlight itself takes more than 5 hours to arrive. So the sun overhead looks like nothing more than an unusually bright star, and you would need a flashlight to find your own boots. What kind of world waits at the far end of a 5-hour beam of light? Gravity is close to the moon's, gentle, forgiving, easy on the body in a way nothing has been since Mars. The temperature sits near minus 220 degrees Celsius, and the ground stretches out as a frozen desert of ice and grey-brown rock. Low hills and shallow valleys, not unlike the dark side of Mercury, the coldest ground this tour crossed near the very beginning. But the cold on Pluto does not behave the way it did on Mercury, and it does not behave the way it did on Titan either. It does not creep in over an hour of failing insulation, giving any warning at all. At minus 220 degrees, the suit's own material turns brittle, the way plastic left outside through a hard winter can shatter at the lightest touch. A breach opens somewhere in the shell, and that is the whole event. Not a slow failure, an instant one. Survival on Pluto, about 8 minutes. And with that, the challenge that opened on the warm, rust-coloured dust of Mars, 10 hours, and a walk back to a waiting spacecraft, closes here, on the far frozen edge of the solar system, on a world where the suit itself is the thing that gives out first. 12th stop, the last one of the survival tour. 10 hours on Mars, 20 minutes on Venus, 15 minutes on Mercury, under 3 minutes falling through Jupiter, 15 minutes again on Europa, 5 minutes falling through Saturn, 2.5 hours on Titan, still the longest survival of them all, 3 to 5 minutes on Uranus, and 2 moons where the danger was never a clock to begin with, 2 minutes on Neptune, the fastest death of the whole tour, and 8 minutes on Pluto, the last number on the board. No two of those 12 deaths looked anything alike from the outside. A crushing wall of pressure. A 6-month night nobody could wait out. A fall with no bottom to hit. A moon manufacturing the very air that killed you faster than any lack of it could. Winds too fast to survive, and cold too fast for the fastest suit ever built to survive it either. Every world found its own particular way in, and underneath every single one of those 12 deaths, something else had been running the whole time, quietly, the same 2 things, prison in every suit on every world, whether the number on the clock read 10 hours or 2 minutes. Radiation was there on the dust of Mars and in the freefall through Neptune's clouds alike. The wrong gravity was there on Titania's drifting slopes, and it was there in its own way, even on Mars, wearing the body down without ever announcing itself. The tour is over, the last suit is silent on the far edge of the solar system, and what had actually been doing the killing underneath every single one of those 12 very different deaths had not been explained yet at all. 12 deaths, and not one of them explains what was actually happening underneath. Strip away the pressure, the wind, the cold, the crushing weight of every atmosphere this tour crossed, and only 2 things are left standing: radiation and gravity, either missing outright or arriving in the wrong amount. Every death in this tour ran through one body and every question still to come about living somewhere rather than just dying there runs through that same body too. So before asking where a person could stay, it helps to ask plainly what these environments actually do to someone. We tend to picture space itself as the danger, the vacuum, the cold, the distance. It is not really. The vacuum is survived with a sealed suit. The cold is survived with insulation. What is far harder to answer for is what a human body does quietly on its own when it spends real time somewhere that is not Earth. Radiation is the quiet one. It carries enough energy to break DNA directly, snapping strands inside a cell the way a hand might snap a wire, and the damage does not always announce itself. Cataracts years later. A slightly higher chance of cancer decades on. Sterility discovered only when it matters. Most of what radiation does never shows up on the clock the way a suit failure does. It shows up in a life. But there is a fast version too. A large dose delivered all at once, above about 0.7 gray, a unit for how much radiation energy a body actually absorbs, triggers what doctors call acute radiation syndrome. The dose that kills half the people exposed to it within 30 days sits at roughly 4 to 5 sieverts, or 4,000 to 5,000 millisieverts. The severity climbs in steps. About 1 gray drops blood cell counts. About 5 grays bring vomiting, and the gut itself starts to fail. About 20 grays and the brain and muscles stop functioning within hours. That last number is the actual mechanism behind 2 of the tour's own deaths. The radiation that ended things on Europa and on Mercury. For scale, a typical astronaut absorbs somewhere between 50 and 2,000 millisieverts across an entire mission, and 1 millisievert is roughly what a person gets from 10 chest X-rays. Even the low end of that range is several hundred X-rays worth of exposure, spread quietly across months rather than delivered all at once. A single major solar event could deliver far more than that in hours. In August 1972, one such storm erupted in the gap between 2 Apollo missions, with no crew anywhere near it. Had a crew been outside a shielded vehicle when it hit, the dose could have been lethal within the time it took to notice something was wrong. This is also why the tour kept describing radiation as something that seeps into electronics rather than something that simply strikes them. When a charged particle punches through a microchip, it leaves a trail of charge behind it, enough to flip a single stored bit, a soft error engineers call a single event upset, or enough to short the circuit outright in what's called a single event latch-up. Neither event needs a crack in the casing or a wire coming loose. The particle simply passes through, and the damage is already done on the other side. A single solar storm in 1989 caused about 37 recorded upsets across satellites, parked in geostationary orbit, machines with no visible fault anywhere on them, just quietly corrupted from the inside. The unsettling part is that the same particle doing that to a memory chip is doing the equivalent thing to a person standing nearby, snapping strands of DNA in every cell it happens to cross. Something else was happening. Every world in this tour killed through a failure. A cracked visor, a collapsed suit, a cooling system giving out. Something broke, or something went wrong every single time. Radiation does not need either. No breach, no mistake. It passes straight through metal and flesh alike. Walls, hulls, skin, all of it equally transparent to it, doing its damage in total silence, and some of that damage will not surface as cancer or organ failure for years, long after anyone remembers which world caused it. The wrong gravity is the second enemy, and it works in the opposite direction, slow and relentless rather than sudden. Not a flash of overwhelming force, a drain that never stops. In microgravity, Bone, the body, decides it no longer needs, simply dissolves away. Astronauts on the space station lose roughly 1 to 2% of bone density a month in weight-bearing bone. So a 6-month stay costs about what a postmenopausal woman on Earth loses in a full year. And the lower spine and hip lose faster still, dropping by about 6.2% over that same half year. Muscle goes even quicker, down 10 to 20% within weeks of leaving Earth's pull behind. None of it hurts while it is happening. That is exactly what makes it dangerous. An injury with no pain signal until a bone finally gives out somewhere it should never have failed. Fluid does not adjust gently either. On Earth, gravity constantly pulls blood down toward the feet, and the body spends a lifetime built around that pull. Remove it, and blood pools instead in the chest, the neck, and the skull, raising pressure behind the eyes and producing a condition called spaceflight-associated neuroocular syndrome, swelling at the back of the eye and a shift toward farsightedness that can begin in as little as 3 weeks. In one study of 11 crew members on the station, 6 showed blood flow stalling or actually reversing in the neck by around day 50. One of them developed a genuine blood clot in orbit, hundreds of kilometers from the nearest hospital, treated with self-injected blood thinners, guided over a telemedicine link from the ground. The fixes exist, but only partly. Crews spend about 2.5 hours a day working against their own bodies, a resistance machine, a harnessed treadmill, a stationary bike, just to slow what gravity's absence is doing to them. Shielding against radiation favors hydrogen-rich material, polyethylene, water, even the ice a suit might carry, over plain metal, since aluminum can shatter incoming particles into a spray of secondary ones that make the dose worse, not better. Artificial gravity by rotation has been proposed since before anyone had actually left the ground. One early design spins a station on a 300-meter tether, about the length of 3 football fields end to end, turning once a minute to produce roughly 0.16 of Earth's pull, about a sixth of what standing on the ground here provides. Another spins a 76-meter wheel 3 times as fast for something stronger still. Neither one ever flew, not at any scale that matters, because the spin rates strong enough to help are also strong enough to make a person sick. The inner ear caught between what the eyes see and what the body feels. That is the honest bottom line, and it is the hinge the rest of this journey turns on. Some of what space does to a body has no fix yet. Passive shielding alone cannot stop the fastest radiation coming from deep space, and nothing yet built can raise gravity where gravity refuses to exist. Whether the bone ever fully returns, what actually causes the eye syndrome, whether a spin rate exists that helps the body without wrecking the stomach, all of it stays open. We don't fully understand any of the 3 yet. Radiation and the wrong gravity were present under every single one of those 12 deaths, whichever suit finally gave out and whatever the clock said when it did. They will be present under every answer that comes next too, because every answer that comes next is really the same project. Engineering around 2 enemies that have never been fully beaten anywhere humans have actually gone. What follows is not another way to die. It is the story of people trying to build something survivable anyway, starting with the world this tour already opened on. The world this tour opened on turns out to be the world where the answer starts too. 12 deaths in, the question has been how fast a place kills you. From here it flips. Could anywhere in this tour be made to keep a person alive on purpose, not for 10 hours or 2.5, but for good? Elon Musk argues that a species confined to one planet is a species one catastrophe away from ending for good. That a second world is not ambition, but insurance against a future where Earth alone stops being enough. SpaceX has put a number on that insurance, a self-sustaining Mars city of about 1 million people, built from roughly 1,000 Starship vehicles over about 20 years, aimed at 2050 as of August 2026. Most analysts who track the company's record think the schedule runs 5 to 10 years optimistic. Ambition and deadline are two different things, and this project has always leaned harder on one than the other. Mars has not gotten any friendlier since the tour left it. Wind still piles fine dust onto anything with a flat surface, solar panels included, enough to choke a colony's power the way it eventually choked the solar-powered rover that died in a 2018 dust storm. Average surface temperature sits around minus 60 degrees Celsius, cold enough that nothing about a colony's first winter is going to feel like a compromise. The magnetic field is barely there. The air overhead still lets cosmic radiation through almost unfiltered, and the atmosphere itself is a poisonous mix of carbon dioxide, nitrogen, and argon, nothing a lung can use. And the gravity, weak enough that a body drifts toward the same slow bone loss the last section spent so long explaining, hands every colonist hours a day on an exercise machine as the price of staying upright. None of that changes just because the goal changed. A colony does not get a gentler planet. It gets the same one, indefinitely. So Mars still kills. What has changed is the question. Not how fast. Whether a person could stay long enough for any of it to matter. Every candidate in the survey that follows will be judged against that same shift. Not the speed of a death, but the durability of a life. Getting there first means crossing a genuinely enormous gap. Earth and Mars average about 225 million kilometers apart, closing to as little as 55 to 62 million kilometers when the orbits line up well and stretching to nearly 400 million when they don't. Drive that average distance non-stop at highway speed, and the trip takes on the order of 250 years, several lifetimes laid end to end just to cross the empty space between the two worlds. Nobody drives it, of course, but the number is there to make the scale land. Because the planets only align efficiently once in a while, a practical launch window opens roughly every 26 months. Miss one and the next is nearly 2 years away, an entire mission's worth of hardware and crew sitting idle, waiting for the geometry to come back around. The vehicle built to close that gap is Starship, the largest rocket ever assembled, bigger than anything that has ever left the ground on this planet. The current stack stands about 124 meters tall, taller than the Saturn V that once carried astronauts to the moon. Its booster carries 33 engines producing more than 16 million pounds of thrust, over double what the Saturn V produced, with 6 more engines on the upper stage taking over once the booster falls away. Fully reusable, it is designed to lift about 100 tons to orbit, closer to 200 if the hardware is thrown away instead of recovered, and up to about 100 people at a time on an actual interplanetary flight. Scale, in other words, is the whole strategy. A colony of 1 million people is not built one capsule at a time. It is built the way a city is built. In bulk, on a schedule, over and over until the numbers stop sounding impossible. Historic trajectories put the trip at roughly 7 months. A 2025 study found that Starship's fuel capacity could compress that down to somewhere between 90 and 104 days on the right path. A difference that matters for more than comfort, since a shorter flight keeps a crew's radiation exposure within career limits that a 180-day flight would not. Every extra week in transit is another week of the same radiation the last section spent so long detailing, unbroken by any atmosphere or magnetic field at all. As of 2026, SpaceX is aiming the coming transfer window at an uncrewed test first, roughly 5 starships. Some reportedly carrying humanoid robots instead of people, proven out before anyone risks a crew on the same trip. Musk has put the odds of that attempt succeeding at 50-50, in his own words, as of August 2026. Not a confident number. An honest one. But here's the part that actually decides whether any of this becomes a colony instead of a very expensive visit. The hardest problem was never the 7 months out. Not the distance, not the landing, the trip home. The fuel for the return flight cannot be carried from Earth. It has to be built on Mars itself, out of the planet's own thin, toxic air and its buried ice, before a single crew member is allowed to leave. The method is called the Sabatier reaction, a way of forcing two gases to recombine. And in plain terms, it means running carbon dioxide and hydrogen over a catalyst. A heated surface that drives the reaction without being used up itself, somewhere around 300 to 400 degrees Celsius, until they turn into methane and water. Methane and oxygen are exactly what a Starship engine burns to lift off. So the reaction is not a side project, it is the return ticket itself. Assembled molecule by molecule out of a planet that would rather suffocate you. The carbon dioxide comes straight from the atmosphere overhead, already 95% of it to begin with. The hydrogen comes from splitting Martian ice apart. The water that comes out the other end gets split again, into oxygen to breathe and burn, and more hydrogen, fed straight back into the loop. NASA has already tested the basic chemistry in miniature on the Perseverance rover, proving the reaction itself works. Proving it works at the scale a single departing starship actually needs, unattended, on another planet, is a different and far larger question, and nobody has answered it yet. Everything downstream depends on that answer. If a fuel plant can run itself and fill its own tanks between landings, ships arrive nearly empty, refuel where they stand, and leave again, and the mass a rocket has to haul from Earth collapses. If it can't, every future crew is stuck waiting on tanker flights of pre-made fuel from home, and the flexibility that turns a landing into a colony disappears with it. A bolt tightened correctly on a chemical plant, tens of millions of kilometers from any help, is what actually decides whether Mars ever gets real traffic or stays a single remarkable stunt. Landing, in other words, was never going to be the hard part. Getting the fuel to leave again is only the first proof the planet demands. Long before anyone worries about the flight home, the same settlers still have to find a way to breathe, stay warm, and eat, using nothing they did not bring with them or build out of the dirt underfoot. Getting there and getting back turn out to be rocket problems, solvable on paper with enough fuel and enough patience. Staying is a different kind of problem, and a much slower one to solve. A colony only counts as living there if the people inside it can breathe, shelter, and eat without a single supply run back to Earth, indefinitely, not just long enough to plant a flag and leave. The first of those three starts with the same air that would kill an unprotected person in minutes. Mars's atmosphere is still roughly 95% carbon dioxide, the gas that suffocates an unprotected human fast. It is also, conveniently, almost pure feedstock for an oxygen machine. NASA has already proven the principle works. MOXIE, bolted onto the Perseverance rover, ran 16 times between 2021 and its final run in August 2023, pulling carbon dioxide out of the thin Martian air and splitting it into breathable oxygen at up to 12 grams an hour, over 98% pure. Across every run combined, it made 192 grams total. NASA is blunt about what that number means at colony scale, about what a small dog breathes in 10 hours. MOXIE was never meant to keep anyone alive. It proved the chemistry, nothing more, and the machine that actually supports a colony still has to be built, one that runs continuously instead of in short test bursts, liquefies what it makes, stores it, and keeps making it unattended for years at a time. The same trick showed up a section ago. Wrapped around the fuel a departing ship needs to make for itself before it can ever leave. Here it repeats, on the air a crew breathes instead of the fuel that gets them home. Not a gas to seal out, a resource to harvest, all day, every day for free, for as long as the machinery holds. Shelter has to answer a different threat first, and it is not the cold. Unshielded, the surface delivers somewhere around 240 to 300 millisieverts a year, close to the same range Curiosity's own instrument clocked back at the very start of this tour, and long-term exposure at that level is considered the single biggest threat to anyone actually staying, worse over years than the cold or the wind ever managed to be. The fix is not a stronger suit, it is dirt. Regolith, the loose, broken rock and dust that covers the whole surface, piled about waist to chest deep, roughly 1 meter to 1.5 meters, brings the annual dose back under safe thresholds, and even a single meter of it cuts the primary radiation by around 41%. A habitat can wear that dirt in more than one way, heaped over a dome, packed against buried walls, or printed straight into the structure itself, and every version does the same underlying job, putting mass between a body and the sky. NASA ran a competition on exactly this problem, its 3D printed habitat challenge, and first place, and $25,000, went to a design called the Mars Ice House, built by the team's Search Plus and Clouds architecture office. It prints Martian water ice straight into the walls and the shield at once, wrapped in a clear film shell, and as little as 5 centimeters of that ice, not much thicker than a folded blanket, cuts UV and gamma radiation down to safe levels. It houses 4 people with hydroponic gardens, crops grown in nutrient-rich water instead of soil, filling the gap between the living space and the ice itself. The idea is a straightforward inversion. The same ice that would freeze a person in minutes becomes the wall standing between them and everything trying to kill them. The way an igloo turns Earth's own killing cold into shelter instead of surrendering to it. Food is the hardest of the three, and here the story stops being reassuring. Musk has said the settlement has to be self-sufficient, food grown on solar-powered hydroponic farms among the rest of it. But here is the reveal that undercuts every hopeful headline ever written about Mars agriculture. No one has ever grown a single crop in real Martian soil. Not 1 gram of authentic regolith has ever been carried back to Earth. NASA's own administrator admitted, in 2024, that the agency had failed to develop a credible mission to retrieve any. An admission that leaves the entire question of Martian farming resting on guesswork, dressed up as data. Every hopeful result anyone has ever read about, every tomato and every stalk of wheat pictured under grow lights, rests on a simulant, dirt built in a lab to resemble Mars chemically, not dirt that ever actually touched it. Those simulant results are genuinely good news, as far as they go. Wageningen University ran crops for 50 days in Mars and Moon, soil simulants side by side, and the Mars mix actually outperformed a nutrient-poor Earth control. Tomato, wheat, cress, and mustard did especially well. A follow-up trial pushed further, growing 9 of 10 crops all the way to an edible harvest. Only spinach failed to make it. For a settlement that has to grow its own food or ship every calorie across tens of millions of kilometers, results like that are close to the best news the whole survey has offered so far. Real Martian dirt hides something the simulants do not carry. Toxic perchlorate salts, a chemical that poisons the nervous system, sit in actual regolith at roughly 0.4 to 0.6% by weight, first found by the Phoenix lander in 2008 and confirmed since by Curiosity about 1 million times typical Earth levels. About 2 years of eating potatoes grown in untreated Martian soil could risk real damage to the thyroid and the kidneys. And the cruelest part is that the early effects can mask their own symptoms. so a settler could be poisoned for months without ever knowing why they felt wrong. Not a trace contaminant. A poison baked into the ground at colony scale. Getting it out means heating the soil to around 400 degrees, close to the same temperature the Sabatier plant already runs its own reaction at, or washing it out with water, or turning perchlorate-eating bacteria loose on it and letting them do the work slowly. And hydroponics alone will not carry a colony past its first years. Soil scientists are candid that a closed hydroponic system can comfortably feed 10 or 20 people and not much more because the pumps, the constant monitoring, and one bad infection wiping out an entire crop all scale against the colony as it grows larger. A settlement with real ambitions, one meant to hold hundreds or thousands rather than a research crew, eventually has to farm the dirt itself, which means solving the perchlorate problem first, at a scale nobody has attempted yet, on a world with no local hardware store and no rescue flight if it fails. Air from poison, shelter from ice, food from ground that still has to be detoxified before anyone can safely eat what grows in it. None of it comes free. Mars does not hand a colonist anything Earth gives away for nothing. It only offers raw material, and a great deal of engineering has to turn that raw material into somewhere a person can actually stay, year after year, without a single shipment from home. None of it was ever going to be simple, and Mars is only the first candidate being asked to prove it can be done at all. Mars will not be the only world asked to pass that same test. 2 candidates sit close enough that reaching them barely counts as a journey, near enough to test before the survey tries anything stranger, and both were quietly enlisted to answer the question Mars never quite delivered for free. In May 2022, researchers at the University of Florida did something nobody had managed before. They put seeds directly into real Apollo moon dust. The seeds were Arabidopsis thaliana, a small flowering plant labs favor because it grows fast and shows stress early, a reliable early warning system in seed form. Each pot held just 1 gram of lunar regolith, about the weight of a paperclip. Drawn from soil the Apollo 11, 12, and 17 missions carried home decades earlier, and that had never once been asked to grow anything. It had sat in storage since men last walked on the moon, waiting for a question nobody thought to ask it until now. Every seed sprouted within 2 days. For a moment, the lunar plants kept pace with the Earth soil controls growing right beside them. Same height, same green, same steady unfolding of leaves. Proof, finally, that the moon is not sterile to life. Then came day 6. The lunar seedlings slowed. They stunted. Their leaves turned a stressed, reddish color, and gene sequencing explained why. The plants had switched on the same genetic alarms a plant raises against salt poisoning and heavy metals. Defenses built for an attack, not a garden. Whatever was in that dust was not neutral. It was actively hostile, and the plants knew it at a cellular level long before anyone looking at them could tell. The regolith itself resisted water, letting it bead on the surface instead of soaking in. Dirt that repels the one thing every growing thing needs most. Not flourishing, not even comfortable, surviving, and only barely. The moon was never going to be a second Earth anyway, whatever grew in its dirt. At about 1/80th of Earth's mass, it cannot hold an atmosphere down at all. Gas drifts straight off into space almost as fast as any process could replace it. And a single day-night cycle there runs nearly 30 Earth days long. Roughly 2 weeks of light followed by 2 weeks of dark. A rhythm no crop on Earth has ever had to survive. Mercury looks like the harder failure by every obvious measure. It is the closest planet to the Sun. Its average surface heat runs around 167 degrees Celsius. Its middays spike past 430. Its nights drop to about minus 180. and it has no atmosphere at all to take the edge off any of it. Nothing between the surface and the raw output of a star. Why test a world that hostile at all? Because the fix for heat and the fix for radiation turn out to be the same fix used everywhere else in this problem. Not a stronger suit, not a thicker dome. Go underground. Since 2011, NASA's Messenger probe has orbited Mercury mapping what is actually down there, and it found vast, smooth volcanic plains, ancient lava that flooded craters more than a mile deep. That flooding happened over 3.5 billion years ago, and now covers about 6% of the planet's surface, an area close to 60% of the continental United States. A scale of resurfacing that dwarfs anything volcanic on Earth's own crust. The same imagery caught something stranger scattered across those plains. Shallow pits scientists call hollows, features nobody has fully explained yet. Together, the plains and the hollows point toward the same hidden structure underneath, a honeycomb of tunnels left behind once the lava drained out. Mercury and the Moon both riddled beneath the surface like blocks of Swiss cheese, solid on top and hollow just underneath. On the Moon, those tunnels are confirmed, some possibly a kilometre or more across, wide enough to swallow a small city whole, and their rock ceilings do work no suit has ever managed. About 1 metre of basalt, the dense volcanic rock both worlds are made of, stops a solar proton event outright. Roughly 6 meters stops galactic cosmic rays, the harder radiation nothing in the earlier tour ever fully solved. Tens of meters brings the dose down below what astronauts already tolerate aboard the space station. Inside, the temperature holds near minus 20 degrees Celsius year-round. No 6-month night, no wild swing between a scorching noon and a killing dark. Just one steady number the whole tunnel agrees on. Building into that rock instead of building a shell on top of it could cut a habitat's launch mass by roughly 2/3, less metal to lift off Earth, because the planet itself supplies the walls. On Mercury, the tunnels are inferred rather than confirmed, guessed at from the same kind of lava plains, not yet seen directly by any probe or lander. But the principle carries over all the same. Proximity to the sun was never really the deciding factor. Here is the deciding factor, and it is the one this survey keeps circling back to. Not heat, not radiation, gravity. You can bury a habitat under enough rock to stop nearly anything radiation throws at it. You can choose a temperature and hold it there for good. Nothing yet built can raise how hard a world pulls on the body standing on it. NASA's own human research program still lists partial gravity as an open question with no answer filed against it, a gap acknowledged rather than closed. Animal studies suggest muscle tissue reliably breaks down below about 0.67 times Earth's pull, and something closer to 0.4 may be the real flaw for keeping a skeleton and a set of muscles healthy across years rather than weeks. The Moon sits at about 0.166. Mercury sits at about 0.38. Both fall at or under that flaw. Not a close call either way, not by 0.1%. Partial gravity does not feel like standing on solid ground with a little less push behind it. It feels closer to still falling, just more slowly, never landing hard enough to tell bone and muscle they are needed. It is the same absence that made a careless push send a body drifting off Miranda's surface earlier in the tour. Only here it is not a hazard to dodge for a few minutes. It is the condition of living there at all, every day, for years, with no minute of it ever pulling hard enough to count as relief. Radiation has a wall now, heat has a wall now. Gravity still does not, and 2 of the solar system's nearest, most reachable worlds just failed on exactly that. Not on distance, not on darkness, not on anything the ground itself contains, but on how weakly that ground holds on. Every problem this survey has solved so far has been solved with mass, more rock, more shielding, more distance between a body and the sky. Gravity does not answer to mass piled on top of it. It answers to nothing engineers have ever tried against it directly. 2 candidates down, and the one enemy still standing is the same enemy everywhere. The next world the survey turns to does not offer a stronger floor to stand on at all. It offers something else entirely, a reason to never put a foot down in the first place. That world is Venus, back in the survey with a case that has nothing to do with what waits on its ground. The planet that killed a suited human in 20 minutes and reduced Venera 13 to silence a little over 2 hours later has not softened in the meantime. Its surface still sits near 475 degrees. The same crushing pressure that collapsed a human chest before the heat could even finish the job is still there, unchanged, unmovable, and the corrosive clouds above it have not thinned by a single degree of mercy. Nothing about the ground has changed, and nothing ever will, and yet Venus keeps getting invited back into this conversation, because underneath the hostility sits a set of numbers no other candidate in the survey can match. Its gravity is close enough to Earth's that a colonist body would barely notice the difference. The same near match that made a suit feel almost weightless on the way down to that fatal surface. Its atmosphere is dense enough to block the radiation that doomed the Moon and Mercury outright. No lava tube required. Its air is almost entirely carbon dioxide, the same raw material Mars needed machinery to manufacture into breathable oxygen. Venus already has the ingredients sitting in plain sight. It is only the ground itself that ruins everything. 360 km/h winds, scouring a surface hot enough that lead would run as a liquid across it. What do you do with a world whose only unlivable habit is its own front door? You stop going through it. 50 kilometers up, above the acid haze, none of the surface conditions apply anymore. Not the heat, not the crushing pressure, not the acid rain streaking through the clouds below. Just altitude, and altitude changes everything. The pressure up there eases to near 1 atmosphere, close to what a person already breathes at sea level on Earth. The temperature settles into a band of about 30 to 70 degrees Celsius. Mild enough a body could survive it in ordinary clothing, somewhere between a warm greenhouse and a hot afternoon. The gravity was never the problem up here either. It was never the problem anywhere on Venus. Not a rescued planet, not a terraformed one. Just enough altitude to step outside the hell and keep everything about this world that was quietly good the whole time. A shirt-sleeve layer of sky stacked directly above one of the deadliest surfaces anywhere in the solar system. NASA Langley has already sketched what living at that altitude would look like, a concept called HAVAS, the High Altitude Venus Operational Concept. Not a base bolted to rock. An airship, drifting in the one layer of Venus's sky that behaves. The crude design runs about 129 meters long and 34 meters across, close to the length of a football field and a half, built to carry a crew of 2, with a smaller robotic version about 31 meters long meant to fly first and prove the design before anyone climbs inside one. The mission is built around a single month at altitude. Aero capture into the atmosphere first, using the thick air itself to slow the ship instead of burning fuel to do it, then the whole structure inflating as it falls, roughly 30 days floating at 50 kilometers, and finally an ascent vehicle carrying the crew back out to orbit and home. Here's the part that sounds almost too convenient to be real. The lift comes from the air the crew is already breathing, ordinary cabin air, the nitrogen and oxygen mix flown on every crewed spacecraft ever built, weighs less than the thick carbon dioxide pressing in around it at that altitude. A balloon needs no exotic gas here. The breathable air itself floats, buoyant purely because it is lighter than what surrounds it. So a hab built to hold the crew's air could stay aloft on that air alone, every cubic meter of it useful living space instead of dead ballast bolted on for lift. Havoc's actual design still leans on helium in the main envelope for extra margin, but the underlying physics runs on nothing more exotic than breath. Being this much closer to the sun helps as well. Solar panels at that altitude take in about 40% more sunlight than the same panels would collect on Earth's surface, more than enough to run the ship's systems and keep the crew's air cool through a month of drifting. None of it is settled yet. Aerocapture into an unfamiliar atmosphere at this scale has never been attempted by any crewed vehicle on Venus or anywhere else. Inflating a structure the size of a cruise ship in the middle of a fall through hostile air has never been tried once, anywhere, by anyone. And the same sulfuric acid that finished off Venera 13 in just over 2 hours drifts through every cloud layer this airship would spend 30 days floating inside. A slow, corrosive rain against the solar panels and the thin skin holding the crew's air in, wearing at both a little more with every pass through the haze. Those are real, unanswered risks, not settled engineering, and no test flight, crude or robotic, has come anywhere close to proving the whole concept end to end. But the core claim beneath all of them does not wait on solving any of it first. The deadliest surface the tour ever measured turns out to be survivable after all, and the entire solution is refusing to touch it. Third candidate down, and for the first time the survey is not fighting the ground at all. It is floating above it. The Moon and Mercury needed meters of buried rock to hold radiation off a body standing on their surface, and even buried rock could not touch the gravity problem underneath both of them. Venus needed none of that digging. It needed a different altitude, nothing more, and gave back one of the widest habitable layers found anywhere in the survey so far, wide enough to hold a floating city for a month at a time without a single wall built against the ground below. The surface is still there, still lethal, still crushing anything that lands on it within hours. It simply no longer matters, because nothing built by this plan ever has to touch it. The next world in the survey barely needs a trick like that at all. Titan barely needs a trick at all. Of every stop in the survey, it is the one candidate that already looks like an answer rather than a problem waiting on an engineer to solve it. This is the same world that gave the tour its longest survival time, 2.5 hours before a suit finally lost to the cold. It steps back into the story now not as a slow death, but as the closest thing to a second Earth found anywhere in the solar system. Titan is a moon of Saturn, but calling it a moon undersells it badly. At about 550 kilometers across, it is larger than the planet Mercury, whose own diameter runs closer to 4,180 kilometers, and about 1.5 times the width of our own moon. It ranks as the 10th largest object in the solar system, counting the sun itself. It only looks modest on a list of moons because it is built mostly of water ice rather than rock and iron. So for its size, it weighs far less than Mercury does, the same way a block of ice weighs less than a block of stone the same size. The resemblance to home runs deeper than size. Titan has lakes, it has seas, it has rivers that feed them, and vast dunes of solid hydrocarbons stacked like sand dunes across its equator, the same family of molecules burned as fuel back home, an energy source lying loose on the ground rather than buried and drilled for. This is the same methane weather already toured once, rain falling from an orange sky into seas that only look like water. The same lakes that carried the tour's own methane reveal. Here, on the return trip, none of that strangeness reads as a threat. It reads as scenery worth settling near. Shoreline and dune and open sky arranged almost like an invitation. What does a moon nearly 1 billion kilometers from the sun, deep frozen and starved of light, have that no closer world managed. Its defenses hold up better than almost anything else in this survey. Saturn's own vast magnetic field reaches out ahead of the moon and absorbs the first hit of radiation before it ever gets close, and Titan's own atmosphere, thick with nitrogen, finishes the job the magnetic field started, layering a second shield on top of the first. Two candidates back. On the Moon and Mercury, radiation had to be solved by burial, meters of rock stacked overhead. Titan solves the same problem from orbit and from its own sky, without a single tunnel dug. Underneath the ice sits an even quieter advantage. Evidence points to a liquid water ocean roughly 100 kilometers down, nearly 10 times deeper than the Mariana Trench, the deepest point in any of Earth's oceans. Water that far down is still water. Split it apart with electricity, an old process called electrolysis, and it lets go of oxygen. Breathable oxygen, sitting in reserve under a moon, most people picture as a frozen wasteland with nothing left to offer. But here's the part that overturns the tour's own verdict. Titan's surface sits at about minus 179 degrees Celsius, the exact cold that beat a suited human's cooling system in the tour and ended in slow hypothermia. That should disqualify it outright. Instead, it does the opposite. Titan's atmosphere is dense enough to spread and dissipate cold far better than thin air ever could, and dense air carrying heat away evenly from a body is a very different threat than dead vacuum offering no protection at all. Not a rigid suit, not a sealed helmet, not a single seal standing between a person and instant death. Heavy clothing and a respirator would be enough. Colonists walking the surface dressed the way a person dresses for a hard Earth winter, breathing through a mask instead of a tank strapped to their back. Shelter follows the same logic. Plastic domes, inflated and held taut by warm oxygen and nitrogen made from the local air and the local ice, standing in for walls of steel or buried rock. The world that took 2.5 hours to kill a fully suited human turns out to be the one candidate in this whole survey where a person could step outside dressed for home. There is a second gift waiting underneath the first. Titan's gravity is only about 14% of Earth's, lighter even than the Moon's, and its air at the surface is roughly 4 times denser than the air over your own backyard. The same density already logged back on the tour. Weak gravity alone lets a body bound farther with every step. Thick air alone does very little by itself. Put the two together and something impossible anywhere on Earth becomes ordinary here. A person straps wings to their arms, no engine, no fuel tank, just muscle pushing against air thick enough to hold real weight, in gravity light enough not to fight back. They flap, they rise, they fly, carried on nothing but their own strength and the thick air pushing against it. Something no human has ever managed under Earth's own pull, no matter how hard the arms worked. Titan is the rare candidate in this survey that gives back more than it takes. Not everything about it is settled. Nobody has lived a year, let alone a generation, under gravity this week. And the long-term toll on bone and muscle at 14% of Earth's pull is still an open question. The same honest gap that dogged the Moon and Mercury earlier in this survey. Titan's own gravity sits lower than either of theirs, which makes the question sharper here, not softer. Nobody has measured exactly how much oxygen a colony's water ice electrolysis could sustain over a real lifetime. Only that the water and the process both exist and wait underground, ready but unproven at any scale beyond a laboratory sample. We don't know yet whether a body can stay healthy that light for decades. We know only that everything else about the place, the air, the cold, the shielding, the shelter, has already answered yes. 4 candidates down now. Air solved by domes, radiation solved by a magnetosphere and a thick atmosphere working together. Cold solved by clothing instead of a suit. Gravity is the one line still left blank on every candidate's ledger, Titan included, and it has been blank since the very first stop on this survey. And still, the one thing no candidate in this survey has fully answered is waiting at the very last stop. A world not handed over by nature at all, but built entirely to order. Built entirely to order means exactly what it sounds like. It is not found. It is not terraformed, or fortified, or forgiven for what it happens to lack. It is manufactured from nothing, piece by piece, until it works. Every candidate so far in the survey has fought the same two enemies with a borrowed hand. Mars borrowed a dome and buried its radiation under a meter of dirt. And even then, a long stay quietly drained bone density week after week. The Moon and Mercury borrowed a tunnel, and lunar seedlings planted in that same borrowed dirt survived without ever truly thriving. Venus borrowed altitude instead of fighting its own ground. Titan borrowed a thick sky and a warm coat. Each of those solutions still answers to the planet sitting underneath it. Its gravity, its air, its distance from the sun, a debt every candidate so far has had to keep paying. The last idea in this survey stops asking a planet for permission. It builds a world instead, and it abandons planets entirely. The concept is called the Stanford Torus, and it is older than it sounds. A 1975 summer study at NASA's Ames Research Center, run together with Stanford University, sketched a rotating wheel-shaped settlement built to house 10,000 permanent residents, close to the population of a small town, floating in space with no planet underneath it at all. Its habitation tube runs about 130 meters across, roughly the length of a city block and a half, bent into a full ring about 1,190 meters wide, a little over a mile around, further than most people would casually walk before breakfast. Nothing about the shape is arbitrary. A ring is the one form that lets a structure spin on a single axis, evenly, forever, without a single moving part fighting another. It solves gravity first, and gravity is the one enemy no planet in this whole survey has ever fully answered. The whole ring turns, once every minute, about the lazy pace of a merry-go-round set to its slowest speed. That rotation presses everything and everyone against the outer rim through centrifugal force, the same outward push that pins water inside a bucket spun in a circle, and at that speed, the push comes out to about 0.9 to 1.0 g, full Earth weight, no planet required, generated by spinning and by nothing else. This is the answer the Moon could not give. The answer Mercury couldn't give. The answer Miranda drifted away from with nothing more than a careless push all those stops ago, could never have given either. Even Titan, the most generous candidate this survey found, still left its own gravity as an open question for anyone planning to stay a lifetime. The ring does not leave that question open. It manufactures the missing weight directly, and whether spinning that fast for a lifetime feels entirely comfortable to the people living inside it is itself still an honest unknown. The same open thread that has followed the gravity problem since it was first raised. Radiation it solves with sheer mass instead of a wall. The finished torus weighs close to 10 million tons, more mass than a small fleet of aircraft carriers welded into a single ring. About 95% of that weight is shielding, a layer roughly 1.7 meters thick, taller than a person standing, wrapped entirely around the ring's outer skin. Most of it is not steel or lead. It is raw lunar soil and slag, the leftover waste scraped out after the useful metal has already been pulled from mined lunar ore. An industrial yard processes that ore from the Moon and nearby worlds, and what gets thrown away becomes the wall that keeps everyone alive. Waste turned into armor. The material itself gets flung off the Moon's surface by an electromagnetic mass driver. a track that uses magnetic force instead of rocket fuel to hurl cargo into space, caught at a gravitational balance point between Earth and Moon called a Lagrange point, and hauled the rest of the way to be assembled at a site labelled L5. None of it is grown, none of it is discovered underground and simply walked into. Every gram is mined, thrown, caught, and bolted into place by hand and machine working together. A colony built the way a ship gets built, not the way a cave gets found. Inside, the design stays deliberately human. About 2/3 of the outer shell is aluminum plating, and the rest is glass set into aluminum ribs, letting real sunlight fall across the interior instead of relying on artificial light alone. Each resident gets a private apartment, stacked across levels and linked by spiral staircases climbing toward the ring's center. And because the whole structure is spinning, anyone who looks straight across the wheel sees their neighbors standing upside down, their own personal down pointing back towards the middle of the ring. A town wrapped around itself with no ground and no sky, only curve. Step outside a front door here and the horizon does not fall away into distance the way it does on a planet. It rises, curling up and over until the far side of your own street is hanging somewhere above your head. 5 candidates into this survey now, and this is the last one. Mars, solved under a dome. The Moon and Mercury, solved underground. Venus, solved by never touching the surface at all. Titan, solved by walking outside in a coat instead of a suit. And now a spinning ring that needed no planet in the first place. The 5th and final answer this survey has to offer. Step back for a moment and look at the whole shape of this journey. The tour that opened this video timed exactly how fast a dozen different worlds would kill an unprotected person. A range running from about 2 minutes to about 10 hours. A countdown that never once favored the person standing on the ground. The survey that followed asked a harder question of those same worlds. Whether any of those killers could be turned, however imperfectly, into a home. Mars, wrapped in a dome. The Moon and Mercury, buried in rock. Venus, held aloft above its own poison. Titan, walked across in ordinary clothing. And the last answer of all, a wheel built where no world stood before it. Here is the reveal that ties both halves of this video together. Not one of those worlds is habitable the way Earth is. Not one of them hands over air, warmth, gravity, and shelter for free. Every single one required someone to notice exactly what would kill a person there, and then to build the one thing standing between that death and an ordinary Tuesday morning. Habitability, it turns out, was never something a planet handed to a species lucky enough to land on the right one. It is something a stubborn, resourceful species builds and then defends, year after year, wrapping a place that would kill an unprotected body in minutes inside enough physics and chemistry and engineering that it becomes barely survivable. Survivable, not habitable, has been the quiet undercurrent of this entire video. First raised the moment a body walked away from Mars alive but slightly worse for the stay, and it finally surfaces here as the whole point rather than a passing detail. Earth is the only world in this entire survey that is habitable by nature. No dome, no tunnel, no spinning ring required, just air and gravity and warmth, given freely, the way no other stop on this whole tour ever once offered them. Every other home in this solar system, present or still only sketched on paper, would have to be habitable by force. There is something quietly enormous in the fact that this can now be said at all. That for every lethal world toured across this video, there now exists a real named answer for how a person could be kept alive there. Air from poison, shelter from ice, gravity from spin, warmth from a coat instead of a coffin. None of those answers arrived by luck. Each one came from someone measuring exactly how a place would kill a human being, then designing the opposite of that, on purpose, piece by piece. We live on Earth stops being the whole definition of the species. It becomes only the first chapter, with the rest of the book still being written, one borrowed world, one built world, at a time, out past the edge of anywhere a person was ever handed a home for free.